Let's dissect the DynamoDB paper today. Amazon published two papers on DynamoDB. One was called Dynamo. It was not about DynamoDB much. The second one is about DynamoDB, the actual DynamoDB implementation, right? So we'll dissect this paper and understand the nitty-gritties of it end to end, right? So folks who are living under the rocks, DynamoDB is world's most popular, to be honest, most popular non-relational database out there. And the core highlight of it is, you would see, like, it is known for providing consistent performance at scale, any scale, right? So a lot of databases are known to give consistent performance, but they typically falter at humongous scale. DynamoDB gives you consistent performance no matter how huge the scale is. That's the beauty of DynamoDB. Just to share some numbers from the paper itself, in 2021, during the 66-hour Prime Day sale, Prime Day that went for 66 hours, trillions of calls were made to DynamoDB. Trillions. Millions is fine. Billion people do parties. Trillions of calls to DynamoDB with peak of 89.2 million requests per second. Just imagine the sheer scale they handled at that time. And at entire duration, DynamoDB didn't go down. It was highly available with a single digit millisecond performance, which means less than 9 millisecond. How amazing is this, right? And almost all the major services at Amazon, like internal services at Amazon, apart from us, the external users of Amazon, even a bunch of internal services of Amazon, they use DynamoDB to store metadata and actually power the actual products of it, apart from us, the customers, right? So what we'll do, we'll dissect this paper into it, understand what it is all about, understand the building blocks of it, understand how it guarantees such beautiful consistent performance, right? Okay, let's start with the first thing. What is the goal of DynamoDB design? How it all started. So DynamoDB started with this just one goal, that it wanted to provide consistent performance at scale. And they didn't want, like, the day zero was more like, hey, we want consistent performance at scale. Like, hey, basically whatever you are guarantee no matter how small the data is, how large the data is, how low the traffic is, how high the traffic is, the performance would be consistent. But then they stretched it up a notch and said, hey, we'll provide consistent performance at scale, and this performance will be a low single digit millisecond. In most cases, less than 5 millisecond. Insane, right? So this is the goal that they started with, and the entire design revolves around this exact same thing, right? Okay. So let's understand the workload pattern, because we would not just like, hey, when we are designing the system, we cannot just start designing it. We need to understand what are the kind of things that we would support, what are the kind of things that we would not support. So the workload pattern that Amazon started with is that they wanted multi-tenancy. That's the most important thing at scale. That, hey, when this DynamoDB infrastructure that they would have would be used not just by internal services, but by external customers. And internal services are also a lot of critical services. They have to ensure that load of one service does not impact the other. This is basically multi-tenancy. That's one. Second, they wanted to ensure high resource utilization. They cannot just have a bloated infrastructure and say, hey, to guarantee single digit millisecond, we just put everything in memory. That cannot be the goal, right? So what happens is they would want a very high resource utilization to keep the infrastructure expenditure to bare minimum. Third is they wanted a boundless scale to tables. Basically, you should not have any limit on how big a table would be. You could have millions rows, you could have billions rows, you could have trillions of rows as well if you wanted, right? Fourth is they wanted predictable performance, be it megabytes of data or terabytes of data. The system had to be highly available, which definitely leads to fast recovery and replication. Sixth is about they want flexible use case support, which means that you should not be restricting to a particular schema, which is where you want, hey, if I support schemaless with basic enforcement, I would be able to support large number of use cases. So this is the kind of workload pattern that suited AWS or Amazon the most, which is how DynamoDB, like with this key goals in mind, DynamoDB was started to be architected. Okay, let's go into the architecture of it. So just to give you a brief of it, DynamoDB has multiple tables. Each table has collection of items. Each item is uniquely identified by a primary key. Now this primary key can have two parts. First is the partition key. Second is the sort key. Sort key is optional. Partition key, as the name suggests, would help you determine which partition your data would go into. So if you don't provide the sort key, partition key becomes the primary key. If you provide sort key, the combination of partition key and sort key becomes the primary key. But you definitely have to provide partition key no matter what, right? The sort key would help you determine that, hey, within this partition, that the data will be ordered by the sort key. So basically it helps you determine the order in which your data is being stored, right? Okay, so this clearly indicates, because of the word partition key, you can clearly see that the data would be partitioned across, or like the data would be partitioned and stored across the nodes, which is exactly what you do. So given an item that you need to store, it is typically passed through some function. I'm not just saying hash function. It could pass through some function that would help you determine which partition your data will go into. Now this partition could be like you could do hash based routing, you could do range based routing. We'll take a look into what type of routing it uses, but be open, could be any routing, right? So given a key, given the partition key, you find which partition it would go to. It would go to that corresponding partition. And if you provide the sort key, within that it would be ordered by the combination of primary key and sort key, right? Okay. So now with this, there is a new feature, like a new thing that DynamoDB supports. It's called secondary indexes. Now here we were only talking about the primary thing, the primary key. But what if, let's say your primary key is user ID and you store user details around that, but now you have to query on the age of the user. So you cannot just do full table scan every time that you would want. So which is why DynamoDB also offers you a support on secondary indexes. On secondary indexes, what do you get is, secondary indexes are literally DynamoDB tables with two columns or n columns, where the first column is the indexed value, while the second column is the primary key. There are other options as well. Go through the DynamoDB documentation to understand those options. But the core idea of secondary index is to have the mapping stored. The bare minimum thing you can do is to store the mapping of the indexed value, in our case, the age of the user, and the primary key. So DynamoDB internally manages that. You don't really have to worry about it, or most databases internally manage this for you. But the thing is that it supports secondary index. So now you can fire efficient queries around, hey, give me all the users whose age is 10. It would give you that, right? So it stores that information as rows: 10, 1, 10, 2, 10, 91. These are users, like user ID 1, 2 and 91 have the age 10, right? Kind of this. Right? So this is just a simplistic representation of it, right? So DynamoDB supports primary key. Primary key has partition key and range key, or sort key. Sort key is optional. Partition key is mandatory. If you provide both, the combination of both is treated as unique. If you provide just partition key, that is considered as unique. Partition key helps you determine which partition your data would go into. It helps you determine the data ownership. DynamoDB also has support for secondary indexes, right? Okay. So given this, let's go a step deeper. DynamoDB table is how it is split into partitions. So DynamoDB table is divided into partitions. We know that. But each partition, understand this, each partition is disjoint, which means no two partitions would share the data. So each partition is disjoint. It is subset of the entire data, and it holds contiguous key ranges. So range partitioning, right? But not really range, but you get it. Once we go deeper, you'll automatically understand. So for example, if I take example of, let's say I have words apple, banana, cat, dog, elephant, fan, grapes, and house, A, B, C, D, E, F, G, H. So you would see partition that looks something like this. Apple, banana, cat goes to partition 1. Dog and elephant goes to partition 2. And fan, grapes, and house goes to partition 3. So sorted key ranges, or basically contiguous key ranges, part of a particular partition. Now, how it would decide where to split, where to go, that's a different problem, which we'll tackle later. But understand what partition is. Here you see that apple is present in partition 1. It means it would not be present in partition 2 or partition 3. These are disjoint, mutually exclusive. But these are subset of data. Your entire data set is what? Apple, banana, cat, dog, elephant, fan, grapes, house. But the subset, each partition holds a subset of data, which is contiguous key range, right? Okay. Now, partition is what a very nice abstraction that they have added, right? That for me, this range is one partition. What DynamoDB does is, in order to ensure that your data is durable, that your data is highly available, that even if one node goes down, it would still work. So what they do is they take the partition and they replicate it across multiple nodes with some replication factor. Let's say I take replication factor of 2, but they typically do it with 3. So doing it with replication factor of 2, let's say I have 3 partitions, partition 1, partition 2, partition 3. I would have 3 availability zone. Availability zone, think of it like data centers, right? I would have 3 data centers on which I am putting or I'm taking one partition, replicating it 2 times in this example. In reality, it is 3, and I would put it across availability zones. For example, the yellow partition is in availability zone 1 and availability zone 3. The pink one is in 1 and 2, and the blue one is in 2 and 3. Here you see, in case one of the availability zone goes down due to any reason, let's say there is a water flood in a data center, you would still be able to serve the traffic from other, right? This is the beauty of it. So to give high redundancy, to ensure high availability, you need to make your data redundant. This is how they do it, right? So no matter if one data center goes down, 2 data center going down is highly unlikely. But if one data center goes down, you would still have other 2 data center to serve the exact same data, right? Now these are called replicas. It's different from read replicas. They are called replicas because it is replica of the data, right? So you have partitions, and these are 2 replicas of the partition, which means these 2 have the exact same data. It's not read replica. I'm making it extremely clear. Read replicas, MySQL world, Postgres world is different. These are called replicas, right? Simple. So partition, so you have data, complete data. Data is split into partition. Each partition has multiple replicas, not read replica. And these replicas are distributed across multiple availability zones for high availability, right? Okay. Now, when you have multiple copies of data, obviously one of them needs to be the leader, other have to be the follower. So out of the 3 copies of data that you have, let's say I have my one partition, which is now split across 3 availability zones or 3 data nodes per se, like could be in same availability zone or different availability zone. That's none of that's nitty-gritties of it, but it needs to be there such that out of the 3 copies of the data that you have, be it P1 is my first partition on data node A, data node B, and data node C. Out of these 3, one of the data node for this partition would be the leader, while the other 2 would be the follower, right? So now what would happen is these 3 are kept in consensus or kept in sync using multi-paxos. They use multi-paxos for consensus. Discussing paxos is a different problem. You can read about it. It's just a consensus algorithm that will help you achieve a lot of stuff. Raft is an alternative for that, right? So multi-paxos / Raft, you should know at least one of them. So just go through in case you are unaware, right? And because you have leaders and followers, there would obviously be some sort of leader election which is happening. In case a follower goes down, a new follower is brought up. In case a leader goes down, one of the follower becomes the new leader. So when a replica detects that the leader is down, what replica would do? A replica would initiate a leader election. That, hey, leader is down, let us elect a new leader. One of the replica would become the leader and it would start serving the request, whatever it is, right? Now understand this. These are partitions and not the entire data, right? So this is happening at partition level, not the table level, right? And there could be many such data nodes, and on each data node there would be multiple such partitions, right? So every single one of them is part of a Paxos group or a Raft group. So they use multi-Paxos for that. But the thing is that they form leader election. This is not node level. This is at partition level, right? So a subset of data, it is at that level, right? Okay. So now, given that we have leader, what's the job of the leader? The leader of a partition, which is this node for partition 1. Data node B can be leader for partition 2, right? That is different. Now, in terms of partition 1, what is the role of a leader? The leader would take care of serving the writes. So all the writes coming to a corresponding partition will be taken care by the leader of that corresponding partition. So in this case, data node C will get the request, and this corresponding partition will be taken, will be accepting the writes. If writes come to P1 or rather data node A and data node B, they would not be doing anything. Right? And the job of the leader is also to serve not just the writes but the strongly consistent reads. Because writes are going over here, this node is in the best position to serve strong consistent reads if required. So in DynamoDB, when you fire the read request, you have two options. Either you say that, hey, I want strongly consistent reads. But the second request says, it's okay if you give me a little bit of stale data. But if you're requesting a strongly consistent data, the read request will be also served by the same data node. Right? So serves the write, serves strongly consistent read by the leader of the corresponding partition. Right? Eventual reads or eventually consistent reads can be served by other data nodes like A and B for partition 1, but strongly consistent read will be served only by data node C. Right? Okay. So now, what happens when write comes to the leader? Right? So when write comes to the leader, this is what happens. So the leader, what it would do is, leader would accept the write it in the write ahead log file on its machine. So data node C is the one where the write request came in because it holds the leader for partition 1. So if my write is for partition 1, it would come to data node C. Data node C would write it to its write ahead log, which is this. And then it would send the write to the other two nodes that serve the replica of the same partition. So replica of the partition P1 is served by data node A and data node B. So data node C would send request to data node A and data node B about the new incoming write for partition 1. Now data node A and data node C would write it to their own write ahead log. So they are not making changes to the table data itself, like in the partition data itself. They are registering this incoming write in a write ahead log file. Basically, durability purposes, that instead of waiting for them to change data into their table, it is better that they just make an entry of that write and they respond with and they acknowledge it that, hey, we have made an entry in a write ahead log file. And once your data node C, the leader of this partition, gets the acknowledgement from both of them, basically attains the quorum, it primarily what it does is it responds back to the client, write is successful. So this is all happening synchronously, right? So synchronously the request came in to data node C for partition P1, which is the leader. Here it makes an entry into its write ahead log file. Then it sends the request to data node A and data node B because they own the replica P1. Synchronously, your client is still waiting for a response. They make an entry into their corresponding write ahead log file and they respond back, done. And then your data node C responds back to the client, write is successful. Right? Then asynchronously, these data nodes would take write and apply it over here. That's a different thing. Right? So changes on the table, changes on the actual data will be done afterwards. But when the write request comes to the replica, to the followers, they simply register it in the write ahead log file and then apply it asynchronously to the actual table data. This way what happens is you're not waiting for, because making changes to the actual data might require you to rebalance the B plus tree in case you are using that. So they're not waiting for it. What they're doing is they're simply registering the write, the incoming write that is happening and then acknowledging it. This way you can get very quick acknowledgement while ensuring durability over here and you can immediately respond back to the client. Right? In the write ahead log file that you get, the write ahead log file on each of these instances, you typically register all the operations that you are getting. Put a key, delete a key, whatever the operation is, they all are getting registered over here. Right? So all the incoming write operations are registered in the write ahead log file on each of these instances and then they are asynchronously applied to the actual table data that you are storing. Right? This is how your write works in DynamoDB. Now, let's take a look. We're talking so much about partition. Let's take a look at why this abstraction is so important. Why did DynamoDB introduce this partition exception? Why can't they just store the entire table in one data node? What's the problem? Why do they have to split the table logically and now in this case even physically into quote unquote partitions and then distribute it across the cluster? What advantage do they get? So the advantage they get over here is, let's say I have partition 1, partition 2 and partition 3. For each one of them, I have two replicas, R1 and R2. So this is partition 1 replica 1, partition 1 replica 2. This is partition 2 replica 1, partition 2 replica 2, partition 3 replica 1 and partition 3 replica 2. Right? You have a table being split into partitions and each partition being replicated n number of times, 2 or 3 or 5, and then they are distributed across the node. Like, what advantage would you get with this? So you get advantage of high availability and fault tolerance. We all agree to that, right? That because you have multiple copies, even if one of the node goes down, you are able to serve it from other. But beyond this, what else? The best part over here is, because of this abstraction, what you can do is, in case a partition is becoming hot, you can actually split this partition into half or basically whatever fraction you want to, and you can then move it across different physical servers, across different data nodes that you have. So in case this partition is going hot, what you can do is split it into half and put it across two nodes. So let's say node 1, there is this partition which is becoming piping hot. You split this partition into half and move and keep the first half in node 1 and move the second half to node 2. This way you would be able to handle the load of a partition very easily. You can split it and distribute it if you want to. Right? The way you split it depends on your use case or how or on which key would you want to split. Do you want to split it in exactly half or 3/4 or 1/4 or whatnot? It's totally up to you, or basically totally on the incoming workload that exists. Right? There is no such hard and fast rule per se over here. Right? But now the beauty is, because of this, your table can now elastically scale without any problem. Because now when a partition becomes hot, you split it in half, distribute the workload. If one of this partition is in, you break it in half and distribute it. Simple. Right? This abstraction is so important for DynamoDB. And it gives you that nice flexibility, because you don't expect your entire data of a table to be present in one node. Because you're splitting it into partitions, you can distribute it across the cluster and you can leverage the actual network bandwidth of each one of those machines very, very easily. Right? So DynamoDB typically does that. Apart from that, DynamoDB also takes care of partition rebalancing. So on every single data node, it has very high observability setup, like measuring CPU, memory, disk and whatnot. A lot of metrics being done. So DynamoDB proactively sees, hey, this data node becomes hot or now looking hot. Let me take some partitions from this node, move it to other. Does this seamless migration of partitions here and there. Because of this abstraction, this one simple abstraction, they have made things so much elastic, which is exactly what you need from a truly horizontally scalable service. But now, does this mean, like, for how long would we keep breaking this partition? What if one partition becomes one row? You typically don't go that deep. What happens is, in some cases, it is futile to split the partition further. I'll give an example. Let's say there is this one key in this one table, which is piping hot. It is accepting huge number of writes coming in for that particular key. I'll give an example. Let's say for a social media post, let's say some social network stores the social post in DynamoDB. A huge celebrity posted something. Everyone started liking that. A huge number of writes started coming to DynamoDB, where the like count is getting ++. Now, if you look carefully, in this entire partition, there is only this one celebrity which exists. Now, which means that only one row is piping hot, not everything else. So why would you split it at one row level? Because it does not make sense to split it at one row level. So DynamoDB does not just keeps on splitting forever, right? So it understands that, hey, do I need to split? Like there should be this bare minimum number of rows that qualifies a partition to be a partition, or it does not split. That if it is not the entire partition, is just one key is hot, it does not make sense to create just a partition to hold that particular key, because after some time that load would go away. Right? So understanding when to make that split, so important. Right? So DynamoDB does not just keep splitting forever. Right? Okay. Now the next part. Let's go a level deeper. Let's see what the storage node holds. We were just drawing this boxes. Hey, this is partition. Hey, this is write ahead log. Hey, this is that. Right? Let's go a bit deeper and see what this is. So each storage node has multiple partitions, right? Each partition is a combination of a binary tree and a write ahead log file, right? So binary tree is the one where the actual data is stored. B plus tree or binary tree, B tree. So B tree is a really good data structure for databases, because it gives you order, log n, lookups and all. You can search more about it about the advantages of using B-trees to store data because of its consistent performance and data being stored where and what. But what it does is DynamoDB typically stores all of this information, all the data in a B-tree, and it has write-ahead log for the obvious durability purposes. So when a write is received for a particular partition, on that partition for that corresponding log, in that corresponding log file, the update operation is registered, and then the changes are applied to the B-tree on that particular partition, the actual data, right? So each storage replica looks something like this. These are storage replicas. Then in DynamoDB, there is also something called as log replica. So log replica are storage replica without the data. Log replica only contains the log file, the write-ahead log file. It's typically there to help you recover quickly. Recovering from data failure takes time, especially when you are recovering the actual data. So which is where you quickly add a log replica so that you can start accepting writes, and writes are distributed and registered so that you get fault tolerance out of the box, right? So storage replicas and log replicas. Storage replica contains the actual data and the write-ahead log file, while the log replica only contains that for this partition, this is the log file. Right? So that is log replica. We'll touch upon log replica when we talk about high availability. Right? Okay. So remember log replica for that. Now, let's go a little level up. Now what we'll do is we'll take a look into different microservices and the responsibility that makes up DynamoDB. It's going to be a huge section. We'll talk about each and every microservice that DynamoDB has and how it helps you ensure the consistent performance at scale. So, our classic high-level quote-unquote diagram for DynamoDB looks something like this. You have authentication and authorization service, you have a metadata service, you have your storage layer, you have your router layer. This is your end user or the client that you have, right? Let's understand what each of this service does, and then we'll talk about each one of them in depth. The first one is the metadata service. Metadata service is one of the most critical services for DynamoDB because metadata service holds the metadata. Basically, which partition is present on which storage nodes. The routing information is held by metadata, right? So that your router basically receives the request from the client. Router takes help from metadata to understand where to route the request to. Then it routes the request to the corresponding storage node, and the storage node writes in the write-ahead log and does that quorum thing, replica, acknowledgement, respond back to the user, right? So this is what happens upon every single write that happens. So your client always talks to the router that you have. The router takes help of metadata to know where to forward the request to. It forwards the request to that corresponding storage node for that partition, writes it in the write-ahead log file, and updates the data over here. Before that, it would do replication across the replicated units or the replicated partitions across the cluster synchronously, right? That same flow, copy paste, goes over here, right? That is request routing service. So request routing is the front facing thing where all the request comes in. Storage service is the one that takes care of all the storage thing across storage nodes and replication and ensuring that the end replication factor for each partition is met. All of that goes on the storage side of things, right? We'll talk about each one of them in detail. One of the most critical services of DynamoDB is the auto admin service. So think of auto admin service as your orchestrator service, which is the central nervous system of DynamoDB. Auto admin, as the name suggests, it's an administrator service which is in autopilot mode. So it basically takes care of, hey, is everyone doing their work properly or not? Hey, is my fleet healthy? Hey, is this partition healthy or not? Hey, is this partition, if this partition is configured to be of replication factor of 3, do we have 3 replicas for this partition or not? Hey, is this node, is this not getting hot? If it is getting hot, split the partition and distribute it and whatnot, right? It takes care of auto recovery from failures. It takes care of load balancing, load balancing offload on the storage side. It takes care of fleet health and everything around it. So it's the master orchestrator that takes care of your entire system, right? While on your reads and write path that you have, the request comes to router service, goes to storage, gets the response, sends it back. This is the bare minimum that you need to do. But to keep everything up and running, it's the job of your auto admin service. Apart from that, there are a few other services. One for transaction management, one for lock management, which takes care of remote locks for in case of transactions. You have auto admin, you have backup and restore. DynamoDB has support for DynamoDB streams, where all the updates that are there are flown to the stream, so that are flown to Kinesis or SQS, so that you can consume from that stream and then reapply changes wherever you would want. All the fancy features are, each one of them is their own corresponding service. Now let's go deeper into implementation of each one of them. We'll start with the first one. This is a huge one. Metadata service. Metadata service was this component. So metadata service is one of the most important services in DynamoDB. What happens is request coming from user goes to the router. Router consults metadata to understand, hey, where do I need to forward a request to? Metadata responds, hey, please talk to storage node 2. Your router then forwards the request to storage node 2. Storage node 2 does that processing, sends a response to the router sends a response to back to the user. So here you see the criticality of metadata service because it owns the metadata, the data about the data. So metadata service holds the most critical mapping about, hey, this is a table. In this table, these are the partitions. This partition owns this particular key range. This particular key range is present at these storage nodes. All this information is stored over here. So for each table in DynamoDB, you have this table has these partitions. Each of this partition has this is owned by this range. This range is present in these storage nodes. These are the replicas. Out of this is the leader and this is not. All of that information is part of your metadata service, right? So now you would think that, hey, when I'm getting this request, like obviously router is not storing any data up until now. Router is using metadata service to know where to forward the request to. So router uses this to do that. But now if you think carefully, if for every incoming request, be it read or write, if router has to always consult the metadata service, you would never get a consistent performance. You would never get high performance system because every time you are getting the request, you are making a network call to get this thing and process it. So what would you do? This is exactly what DynamoDB does. It caches the routing information locally on the router. So when a router receives the request, it sees it if it has the routing information for that corresponding party, for that corresponding key or for that corresponding partition. If yes, it would use that to forward the request to the corresponding storage node. If not, it would go to the metadata service, download the corresponding routing information for that table and keep it here cached locally on the routing server. And then use that information to forward the request to the corresponding storage node. That's the bare minimum that you would think you'd do, right? And that's exactly what DynamoDB did. So DynamoDB started caching the table routing information on the router lazily. So if the request comes in, then it does that. And there is an eviction. So after some time, this would be deleted and whatnot. All of that handy, right? Okay. Now, if you think about it, the routing information would not frequently change. How frequently would a partition be changed from one node to another? Not so frequently. So here, what DynamoDB observed a cache hit ratio of 99.75%. Which means that most of the requests that came to the router was served directly from locally. It was not serving the data. It was a routing information. That where should I forward the request to? Not the data. The routing information. Right? So request came to the router already had and it forwarded the request to the corresponding storage node, get the data, send it back to the user. Right? Router cached the routing information, not the data. Data caching is different. This is routing caching. Right? Okay. So they did this. Now because you see very high cache hit ratio, what would happen if this invalidates? What would happen if, let's say, my router service restarted all the nodes all of a sudden? What would happen? The incoming request would come to this router. Router would not have anything cached. What's the fallback? They would all call metadata service to get the response. Metadata service would send the routing information. So now, in case the router service reboots, in case there's a huge cache miss, all of this would fall back to metadata service, spiking the traffic on the metadata service. Right? It spiked the traffic on metadata service and that would crash the metadata service. And if metadata service crashed, there is an outage. Because the router is very heavily reliant on metadata service to know where to forward the request to. So what do you do? To prevent this from happening, because this is a huge pain. In case your router service restarts, in case cache invalidates, there is a huge spike on metadata service. This would break things. So what's the solution? The solution to this is what Amazon did is Amazon actually built something called as a MEMDS, a memory data store, an in-memory remote distributed data store, which is optimized for range queries. For example, given this key, find which partition would it hold, or rather find which partition does it hold it. From that partition, you'd know which storage node does that partition that partition is present on, right? So MEMDS is an in-memory distributed data store that stores data in memory. It is not a persistent storage that stores data in memory, which is used by metadata, like it uses metadata service to get the data and whatnot. There is one more flow. I'll talk about that. So here what is happening is the request is coming to router. Router has some data cached locally that still exists. But if it does not have the data, it goes to MEMDS. MEMDS is a distributed in-memory data store whose job is to hold the routing information, but it is optimized for range queries. Basically, less than this key, greater than this key, floor function, seal function. It is implemented using Patricia plus Merkle tree combination. It's a hybrid combination of both, right? Because you know how Merkle tree would help you find what changed, like if there is any change. And Patricia tree has its own set of properties. So these structures help you fire efficient range queries, right? So Patricia is typically, it basically gives you efficient range queries. So what happens is, given a key, let's say I want to find value for key cat, where would I have to go? I have to go to node 1, but how would I know where would I have to go to node 1? So the way the MEMDS is distributed in-memory data store, optimized for range queries, you fire the query to MEMDS. MEMDS would give you the answer, which node would you, or which node should you go to. That's the job of MEMDS. It does that, right? This way, what you do is, instead of you relying on, or rather your router relying on metadata service to fill the data or to populate it, it actually calls MEMDS to get the data, right? That's a huge advantage. Because now you are not directly dependent on metadata service to get that information. You are relying on some other component, but MEMDS is in-memory data store. You can very quickly get it. Plus MEMDS is optimized for range queries, which is exactly what your purpose is, right? So router uses MEMDS to get which node should you go to, and then it basically makes the call over here. But router still has things cached locally. So it might not for all requests would have to go to MEMDS to get the information, right? Once, yes, not all the times, right? Okay. Now, one key thing. I just said that router service does not always go to MEMDS, but that's not true. So the flow is, MEMDS is a distributed in-memory data store. Now what you need to ensure when you're building a highly available system, that there in no point, in no case, your system is going down. Now, typically, when does a system go down? A system goes down when it sees very high load, right? And it is not provisioned enough to handle that load. Assume that your system is horizontally scalable. Let's say your system is horizontally scalable, but because you were caching things locally, you thought, hey, let me keep only 2 instances of MEMDS over here. Why do I need 20? But if this goes down due to any reason, or if this cache invalidates, a huge amount of load will come to MEMDS. Then MEMDS would go down because it had 2 instances. It actually required 20 instances. So the same problem. So what problem was with metadata? Same problem happened with MEMDS. So why are we adding MEMDS then? The reason is that MEMDS is not provisioned to a bare minimum capacity. MEMDS is provisioned for the actual load. For example, anytime the request comes in to the router service, if it does not have the data, it goes to MEMDS, gets the data, caches it locally, and then serves the request, right? But while it is doing that, it would make an asynchronous call to MEMDS. This way, your MEMDS is like all your requests are still going to MEMDS, but not synchronously, asynchronously. You don't do anything with that, but it's just more about preparing, like keeping memds prepared for the high load that would come in case your cache goes down. This is a really important high level design practice, right? For you to build a highly available system, this is a very common practice, FYI, where you are not in synchronous request response, you are not relying on memds a lot, but still asynchronously you are firing requests on memds just to keep it handy. It's more like during wartime, or rather during peacetime, if soldiers are not prepared, and during wartime they would be lazy, right? Then you would not be able to win the war, right? Same thing goes over here, that even though there is peacetime where there is cache hit, there is no need to call memds, but you are still asynchronously calling memds so that your memds cluster is well provisioned and it is used to handling so much of request, right? But because you are doing async, in case it is down or facing some issues, you would know that when you don't want to scale and when you don't want to scale, right? But now who updates the information in memds? The storage nodes update the information in memds directly, that hey, I am the storage node, I own this partition. All of this information gets indexed in memds. But memds is what? Transient, because it stores data in memory. What if that goes down? You have metadata service to serve that, right? It would have some persistent layer. Paper did not mention explicit persistent layer for that metadata service, but there should be one which holds it in a persistent manner that hey, this node owns this sort of partition. This partition is present in this node. This is where the replica lies, right? But this is such a beautiful high level pattern, where you are ensuring that there are no cascading failures no matter what. Now let's take a look at edge cases over here. If all the nodes of router goes down, then anyways DynamoDB is down, right? So you keep this behind load balancer, have some monitoring setup. One node goes down, other nodes takes its place and whatnot, right? If this cache goes down, the requests go to memds. If let's say all the local caches of all the routers go down, what would happen? All the requests would go to memds, but memds is already provisioned to serve those much of load, right? That's the beauty of it, because memds is already provisioned enough to handle that load. Even if all the local cache goes down, your memds is provisioned enough to handle that, which means that there would not be any cascading failures ever. Just by over provisioning memds, you solve the problem of cascading failures. Such a beautiful piece of distributed system, right? But you are still having this local cache so that you don't have to synchronously make call to memds every time to get the routing information and then send the request to. So once it is cached locally, you directly send request over here, but asynchronously you send request to memds. That's the beauty of this design, right? This is how you ensure high availability at all times, right? Keeping yourself up for the wartime. That's how the world of software engineering works, right? Okay. That's about the metadata service. I told you it's going to be deep, right? The next one is storage admission control. Really important. So storage admission control is the part that how much load one storage node takes care, like could handle. This is all about storage admission control, right? So we get a lot of requests. The request at the end has to be served by the storage nodes, but you cannot over bombard, or you cannot bombard a lot of requests on storage node, otherwise it would go down. How do you rate limit that? That's the concept of storage admission control, right? Okay. So admission control ensures that your storage nodes are not overloaded and the requests are rate limited. But how? Let's talk about it. So what do we want is, on a storage node, you would have a small component running for admission storage control, called admission storage control, call it anything, right? But the idea is, first of all, one storage node can host partitions from different tables, right? So let's say I have three partitions A, B and C. It is very possible that these three partitions are not from same table. They could be from three different tables, right? For each table in DynamoDB, you provide something called as a capacity unit, a read capacity unit and a write capacity unit. Think of it like how many writes per second do you want it to support? Simple terms, right? So you can configure that, hey, on this table, I want to support 500 writes per second. On this table, I want to support 200 writes per second. On this table, I provision it for 50 writes per second. You configure it, right? That's the idea behind it. It's up to you. You have to configure it, right? Now, what would happen? is when a corresponding partition gets that much of request, once it hits that limit, it would not allow further requests to be processed. Because rate limiting is essential, because the customer is paying for 500 writes per second. Why would customer call 1000 requests per second? It cannot. It's your responsibility to block and throttle them. That's exactly what storage admission control does. It basically ensures that your storage nodes do not handle more requests than it is provisioned for. Because the day you start firing requests on that and storage node gets overwhelmed, it would crash and your system would have an outage. You don't want that to happen. So which is why rate limiting is really essential. But remember, every single thing in the world has a limit. Even storage node, one physical storage node has a limit. That hey, let's say, I'll take another analogy. Let's say one EC2 instance you have can handle only 10,000 requests per second. Only 10,000 requests per second. That's a physical limit of it. No matter you host 10,000 partitions in that, 1 million partitions in that, or one partition in that. The limit is at the server level. That hey, my server at max can handle 1,000 requests per second. So no matter how many partitions you host, you cannot be handling more than that much of request. Right? And that's exactly what is a global limit for a storage node that you have. So let's say you have a limit of 300 requests per second. So this entire storage node can handle 300 requests per second. Within that storage node, you have 3 partitions and each partition can handle, let's say 50 requests per second. So in all 50, 50, 50 and this entire thing is 300. So it means that there is a way, like there is a possibility that you can add 3 more partitions each handling 50 requests per second into that. You can host it if you want it, right? But there is a global limit for a storage node that you need to adhere to. And there is a local limit to each of the partition depending on what customer has provisioned for that corresponding table, right? This is what you need to ensure. Now, the auto admin service that we talked about, the central nervous system of DynamoDB, what it ensures is that at any given point in time on any storage node, the total amount of request each partition is assigned, because who is assigning capacity to a table? The customer. The customer is saying that, hey, I will handle, like I want 500 requests per second on this table, right? So customer knows how many requests per second each partition will be holding, or DynamoDB knows how many requests each partition is supposed to handle. So the total limit of the storage node, the total global limit of the storage node should always be greater than the summation of the limit of individual partition that it is hosting. So for example, if the storage limit is 300 requests per second, I cannot have 3 partitions each having limit of 200 requests per second, because then it would be 200, 200, 200, 600, but my limit is 300, right? So I cannot host it. So auto admin service ensures that no matter what, one storage node is never assigned the partition whose cumulative limit exceeds 300 requests per second. That's what the job of auto admin service is. It has to ensure. Otherwise, if you allow more partitions, if you are serving more partitions from that, the request would come in and you now have to handle, but you cannot handle, right? So that's the concern. So how do you address that? So now we'll go a level deeper to understand how all of this is ensured. So DynamoDB has concept of read capacity units and write capacity units, right? Now what happens over here? For a particular table. Now let's answer this question first. What is the limit of a partition? Does user know how many partitions a table has? No. User just says, I have this table. This table needs to handle 500 requests per second. That's it. It's DynamoDB is partitioning it. DynamoDB is splitting into 5 partition, 10 partition, 50 partition, 1000 partition. You don't care. As a customer, you don't care. You say, hey, this is the table. This is the limit that I want to work with, right? Which is what you would do. So DynamoDB, what it does is, DynamoDB configures something called as read capacity units and write capacity units. And the idea is simple. That if my table has, let's say, read capacity unit of 1000, right? And suppose DynamoDB chose to split my table into 2 partitions, P1 and P2. So what would happen is I have 1000 read capacity units, like 1000 requests per second to put it in simple terms. and on that table I have two partitions P1 and P2, I would distribute it proportionally. So because I have two partitions, total capacity is 1000. Partition P1 capacity unit will be 500. Partition P2 will be 500. Splitting it equally among all the partitions. So now let's say, suppose due to any reason, yeah. Suppose let's say I am seeing a lot of traffic on partition P2, this partition, and I choose to split the partition into half. What will I have? I will have partition P1, partition P21, and partition P22. Right? Partition P1, partition P21, partition P22. Now what's the RCU distribution across this? It will be 333, 333, 333. 1000 divided by 3. Right? So no matter how many partitions you have, and obviously DynamoDB has different ways. This is the starting point. Right? Absorb these things. So what happens over here is, if my table capacity is n, and if I have m partitions, so each partitions will get m divided by m wala capacity. That's the thing, right? So what DynamoDB assumes is all the keys are equally likely to be accessed. That's not true, but DynamoDB assumed it on day 0, right? But in reality, some keys are more likely to be accessed than others. For example, social media post. Let's say I'm storing the feed of a user or a social media post in a DynamoDB table. More recent posts are more likely to be reacted, like comment, share, subscribe, whatever that is, right? Because it is more likely to be reacted, it would see high read and write requests per second, right? But that is a problem, because now what would happen is, first of all, you would have hot partitions, because the post that have just been published I will get huge reads and huge write request. So what would happen is, let's say one of the post was there, right? One of the post was there, posted by some huge celebrity. The data was lying in partition 2. That corresponding row was in partition 2. That post is published, right? Partition 2 had how many capacity units? 500, because you had 1000. You divide it by 2, you get 500, right? Now what did happen? Partition P2 became hot because of all the reads and writes that were happening on that. Now what did you do? You split the partition into half, P21 and P22. When you split this in half, the hot post would have been in any one of them. Let's say it is in P22 here. But now, what would be the distribution? 333, 333, 333. The problem is, that same post was part of partition 2, was getting 500 as its provisioned capacity, but after splitting, that same post is now getting 333 as its provisioned capacity. So this problem is called throughput dilation. You have diluted the throughput by horizontally scaling it. That's not what customer would expect. Customer would expect, hey, because I'm splitting it, because this partition is hot, I should get the performance. But you just diluted your throughput by splitting it in half. But you say, no, but that's how my system is. Customer wouldn't understand. Customer would say, hey, I'm paying you money. I want performance. I don't care. Right? So, how do you address the throughput dilution problem? That becomes the root cause now. Let's take a look. So, first way of handling throughput dilution is called bursting. In real world, if you look carefully, the pattern is something like this. If I take example of social media, if a post is recent, a huge amount of traffic would come in. After some time, no one gives a crap about that post. Correct? Same thing would happen. That's the exact same thing would happen, right? So now if you look carefully, for a particular storage node, not just table, for a particular storage node, each of the partitions, let's say some throughput, some capacity is allocated to each of the partition. Not all partition would use their allocated throughput simultaneously. For example, each of this partition has 50 requests per second provision. What are the chances that all of them are using 50 requests per, all of them are getting 50 requests per second? Not really, because there is no uniform distribution, or there is a uniform querying of data or uniform query load on all of your partitions on a storage node, which means we have some breathing space. So idea is that given that not all partition would be using their allocated throughput simultaneously. What we can do is we can let some partition tap into the unused throughput capacity of the node. For example, this node has capacity of 150 requests per second. Each one of this is 50, 50, 50. But let's say this is only using 20, or I have this example. Sorry, my bad. I forgot I had this example. Okay. Let's say I have my partition P1, P2, P3, each one having 1000 write capacity units provisioned, right? So it's geared up for 100 writes per second or 100 capacity units. Now what has happened is, but the observed is that P2 and P3 are only getting 20, right? So now what we can do is, if P1 is getting a little higher load, we can allow P1 to go beyond its provisioned, which is 100, and go a little above that. Why? Because P2 and P3 are only using 20 of their 100. You have 80, 160 in buffer. You can let P1 go to like 150, 160, 170, 180, something like that. Right? This is called bursting. You are allowing to support burst request coming in for a particular partition on a specific node. Right? But how do you implement? Everything is about implementation. Drawing boxes is easy. Thinking of implementation is hard. So how do you implement? Implementation is interesting. So what happens? How do you implement this? How do you allow a particular partition for some time to tap into unused capacity of a node? The way you do it, or the way DynamoDB does it, is called as token buckets. Very simple use case. So what do? Is each storage node has a token bucket, which says that, hey, every second this token bucket will be replenished, right? So it would be resetted. Let's say I have 100, or let's say my node has 300 writes per second. So every second the token bucket on this server would have 300, because that's the global limit that I have. So 300 tokens would be there in this bucket, right? Each of the partition would have its own token bucket, the provisioned throughput or the allocated token bucket. That, hey, for this partition 100 is the allocated one. So for P1 it is 100, for P2 it is 100. These are allocated things, right? So apart from that, what you would have is each storage node has its token bucket. Each partition has one token bucket for allocated, while one token bucket for burst. So it's not that, hey, because my machine or my storage node can handle 300 writes or 300 requests per second, I would take it to 290 because other nodes are not even using anything. No, everyone has some limit to that. That is a burst limit. For example, you say that if my provisioned is 100 for a particular partition, my burst would be, let's say, 30. So my partition can have 100 requests per second, but it can handle burst up till 130 requests per second, right? So it has that limit. So now what do? For any incoming request that is coming in, you obviously know which partition it would go to. You get the partition. You check that if allocated for that partition has token or not, which means from its allocated capacity, that partition has allocated capacity of, let's say, 100. So have I used all 100 of them? If not, I would just use that and done, because I'm using from my allocated quota, which is good. If the allocated partition has nothing for that token, or sorry, for that partition, what you would do is you would see if burst has something. If the burst bucket of that partition has some tokens, which means you are allowed to go to that certain level, so you would pluck that out from this burst token and one from this allocated node of this what you have, right? So this way you are allowing 100 requests per second plus some bursting. That is obviously configurable, right? 10%, 20%, 30% bursting is allowed per partition, for example, right? But you should, no matter what, you should never breach the maximum that a storage node can handle. That's the thing. And this is how you handle throughput dilution via bursting. So even though you have provisioned 100 requests per second per partition of you're still allowed to go beyond that in case the storage node on which that partition is hosted can handle more load. Such a beautiful piece of design. I just love it. I love distributed storage, right? You understand the beauty of this. How amazing. And every second the token bucket is replenished. Problem solved, right? Okay. Second way to handle throughput dilution. We talked about bursting, but what if your spikes are long-lived? Bursting is where you see immediate spike and it goes down, right? But what if your spikes is long-lived? Like you see a surge, but it is not short-lived. It would not end up in it would not just finish in 5 seconds. It's long-lived, going for 30 minutes or 40 minutes, for example. I'm just taking random numbers now. Don't take me seriously on that. So to better absorb the long-lived spikes, how do you do that? Bursting cannot handle that for sure. So these are typically skewed workloads, which means, for example, I'll give an example. Let's say you have a DynamoDB table in which you define your partition key as time, date time, right? Now what has happened is the data that you are putting in is partitioned by time. So most recent data will always go to the most recent partition that you have. Now what happens is all other partitions are just vacant. They don't have any load coming in, while the recent one is always going to the most recent one. So these are long-lived spikes that you would get on one of the partition. How do you handle them? So now let's go into adaptive capacity. How do you handle it? So if a table is experienced throttling, but the table level throughput is not exceeded, the idea is, for example, you as a customer of DynamoDB, what you would say is, hey, I have this table, I'm partitioning it by date, let's say day, I'm partitioning it by day, every day has one, right? The data I will write will be per day, right? The data I'm just writing with respect to dates all going to that one partition because I partitioned by day. I configure my throughput capacity to be let's say 1000, right? You would say I have configured my table capacity to 1000 writes per second. I am writing per day basis, right? So if I am writing it that way, why are you throttling me? Because I am paying for 1000 writes per second. I'm writing to your table. I don't know you are partitioning it. I don't care if you partition it. I want 1000 write per second on my workload. I don't know how you do it, but you do it. Very common use case, right? So what happens? This is where adaptive capacity comes in. So let's say the capacity that you have is 1000, right? So let's say you have it. Basically, let me start with that. The adaptive capacity, the plan is for adaptive capacity is adaptive capacity, it adjusts the partition throughput in proportion. So whatever the request that you are getting, it is proportioned. The capacity of that corresponding partition is increased and for other one is decreased because your workload is skewed. This is adaptive capacity, right? So what we studied first is if my table's capacity is set to 1000 and if I have two partitions, each one would give 500, right? But what adaptive capacity says is, hey, I would not split it to 500. What I would split it is, depending on the amount of requests that I'm getting, I would allocate my throughput for that partition in that proportion. That one partition gets 100 while other partition, which is heavy, gets 900, right? But here, the global limit for the storage node would still remain the same. That auto admin service would not allow other huge partitions to be present on this storage node, right? Because the global limit of summation of provision throughput on each of this should be less than the total what a node can handle, right? It would still handle that. It would still ensure that your auto admin service. But what you are doing is you are allocating the provisioned capacity across the partitions of a table depending on the amount of requests that it is getting over long-lived period. It analyzes those metrics and assigns the provision capacity for each partition that you have. This way, you can handle long-lived spikes with adaptive capacity, right? Very nice implementation. I just loved it, right? Okay. We talked about two ways to handle. One way to handle burst. We talked about that. One way to handle long-lived spikes. We talked about that. So the way burst is handled is by using token buckets and having some burst capacity. No one would ever exceed, no matter what, should exceed the total request one node can handling burst. But for long-lived spikes, you are doing adaptive capacity. The concern is that bursting helps with short-lived spikes. We saw that. Adaptive capacity is reactive. It takes time to react, right? So while this is happening, while the requests are coming in, while this table is getting throttled, because it takes time for your adaptive capacity to, adjust the capacity across partition. But while this is happening, your tables have observed unavailability. Because you made the request, your table request got throttled. That's a problem. So your customer, the customer of DynamoDB is not happy, because customer says, hey, I have allocated 1000 requests per second. Why are you not giving me 1000 requests per second? Do something, right? But while this ticks off, while this adaptive capacity kicks off, you are seeing unavailability on tables. Goes against the high availability goal of DynamoDB. So what's the idea? Which is where the concept of global admission control comes in. We talked about storage admission control. Now there is a global admission control called GAC. The idea is, now hear me out on the idea. The idea is that there would be a centrally track of table level throughput, what you have combined. So let's say your customer says, for this table 1000 requests per second is what I'm provisioning. So you would, in your global admission control, you would have 1000 requests per second. That, hey, this table is allowed to process 1000 requests per second. That's what your global admission control would do, right? This is done at request router level. So the request router at this level, what it does is, you have a global admission control which has a bunch of tokens. So request router, it basically what it does is, it maintains a local token bucket and it periodically gets the new tokens from global admission control. So global admission control, for each table it knows what it can handle per second, right? Request router gets the tokens from global admission control. For each request that it gets, it uses one token each, right? When the token exhausts, it gets the next set of token from global admission control, right? This way, your request router, at least at the first step, it allows you to process, it allows you to accept 1000 requests per second. Processing is different, but at least your request router accepted those many things. But if your table fires more than 1000 requests per second, you have provisioned 1000 requests per second, but if your client actually fires more than 1000 requests per second, it would be dropped at the request router level. Here we can clearly see that solves. So at request router level, this problem is solved. But it would have to go, what would happen is that when it goes to the storage layer, then all the things that we discussed at the storage side, right, still holds true. Your adaptive capacity and this and that, it would still hold true exactly like that, right? You're bursting your capacity. So you are not limiting anything. At a global level, you're allowing a request to come in and then you can do retry. You as in DynamoDB can do retry of those requests and whatnot, or staggered way of processing and whatnot below this level. So the idea being, your global admission control takes care of the global requests that are coming in at the request router level, and it takes care of letting the data in. It's a global, kind of like a global rate limiter, you may think of it that way, right? So it would not let your client breach the partition level. So the combination of these three would help you ensure that your storage nodes are not over provisioned. You get enough time to process things. You give the right message to your user that, hey, I'm letting a request in for whatever capacity that you have provisioned, right? The combination of these three helps you address this problem. Okay. Now the next one. The next one is about durability. Next interesting thing. Okay. So durability. What is durability? Durability is about persistence. I'll just store data in the disk. What's the problem? Is there more to durability? Yes, there is. Durability is not just persisting data to the disk. It's much more beyond that. So let's talk about that. So durability is more about, you have to prevent, detect, and correct any possible data issues that you have. Any possible data issues, right? Or whatever could happen, whatever could go wrong, would go wrong, and you have to be prepared for that. Let's take first example, hardware failure. So for example, while you write something to the table, what if data goes down? What if node crashes? What if there's a hardware failure? What if there's a disk crash? Are you able to recover from that? That's the question that you should ask. So what DynamoDB does is, DynamoDB uses write ahead logs for providing durability. We discussed that. Write ahead log is append only log. It keeps appending over that. Once it is appended, once it is there, and then the changes are applied on the B plus tree or the B tree that you have, right? So by using write ahead log, it ensures the fact that the changes are first written in the log file and then applied on the tables or on the data that you have, right? That is one. So in case that goes down, you can recover your semi-processed data from your write ahead log. That's exactly what DynamoDB also does. It's a standard procedure across all databases, right? Now this write ahead log that you have, they are periodically archived to S3. It's really important because what if this data node becomes inaccessible? You should be able to recover that, right? So these logs, these write ahead logs are constantly archived to S3, basically periodically archived to S3, right? But the edge case, what if I have made an entry into this write ahead log, but before I could archive it on S3, what if this data node crashed? What would you do, right? This is where we leverage replication. So remember, a replica, a data of a table is partitioned. Each partition has multiple replica. The write goes to the leader, adds it to write ahead log file, sends it to replica. Replica adds them to the write ahead log file and then responds back to the leader, and then the leader responds back to the client, right? Now here what you do is, if this node goes down before the logs were replicated on S3, what would you do? You have other partition to take care of, like other partition can give you that. So remember, the partitions have replication factor typically of 3. So if a node goes down, a new node is assigned that responsibility. So let's say if this node went down, I immediately spun up the new node. And this new node, as in the auto admin service does that, right? So auto admin service spun up a new node or an existing node, it assigns the responsibility of this part. It says, hey, the replication factor of this is not met. Let me ask another node to immediately replicate the data because now this is fragile. Because if this went down and this went down, you would not have any copy of the data, right? So what do? You typically do it with 3. I have taken example of 2 over here only, right? But the idea is that if this node goes down, immediately a new node starts accepting the responsibility of the node that went down, and it immediately starts copying the data here and there. Immediately, right? But now the thing is that instead of immediately when this starts up, instead of it being a storage node, what it first does, it adds log replica nodes. Remember log replica? Log replica were storage nodes without the customer data, but only the write ahead log file. So what it does is, it immediately adds the log replica of those corresponding partitions. This way what happens is that the writes that come in, because when is write successful? Write is successful when the write comes to the leader. From that leader, it sends it to the replicas. That replica simply adds it to the log files and responds back. They are not ensuring that it is added on the data, which means that if we just have log replicas, then our writes would still work, which is precisely what DynamoDB does. So the first step, when a node goes down, immediately add log replica for that and then take care of data replicas, right? That's the idea behind it. This way you minimize the time for your recovery. That in case a node goes on, you should not take more than few seconds to recover. That's how it does. Such a beautiful thing, right? Okay. On durability, again extending our discussion on the durability thing. A data can go corrupt, which is called silent data errors. Now what are the silent data errors? Silent data errors are data errors which are silent. But no, never mind. Okay. So silent data errors is more about that, hey, when customer thinks that customer wrote that is exactly what needs to be written onto the disk. It should not automatically convert to cat. You say, hey, why would it convert to cat? Bits and bytes over the networks can flip. While writing to the disk, it can flip. There are so many places where things could go wrong that needs to be handled. So across the entire layer, right from your customer over the network into your infrastructure, across the services onto the disk till the level persisted, you have to check for checksums. CRC, cyclic redundancy check. At every single step in your request flow, you would check for checksums. You have to ensure that no matter what, you are never storing a incorrect data, something that customer didn't intend to store. So you check checksum from the customer side all the way to your storage layer at every single step, which is how you ensure, because building databases is not easy. It's really difficult, right? These are some very trivial things that we typically don't think about much, but these are so important in building a resilient data store, right? Okay. Apart from that, even the log files that are archived on S3, they are also piggybacked, or they are also attached a checksum file with that. Just ensuring that what I am intended to store on S3 is exactly what is getting stored on S3. In case there is a checksum failure, do a retry. So you ensure that there are no silent failures in your data. Okay, next point. Apart from that, you handle silent failures, but what DynamoDB also does is it takes care of continuous verification. So DynamoDB continuously verifies the data at rest to ensure that all the 3 replicas of the data have the exact same data. Again, checksums, right? Anything that you read around data integrity is always have to do with checksums, right? It ensures that it is the checksums are there. Apart from that, whatever is archived on S3, what is archived on S3? Log files. It periodically downloads the log files, recreates a replica, and then confirms if the data matches or not. Such high integrity checks DynamoDB has applied, right? In case you have never heard of checksum, you are just a Google search away, but checksum is a very standard way of ensuring that your data is not corrupted, right? Or you detect corruption, you cannot fix it, but you can detect corruption. So then, depending on what your use case is, you can choose how to fix that, right? Okay, the next part. How do you ensure durability? Aggressive testing. So what they do with respect to aggressive testing, at every single step, they do stress test on storage nodes, on API servers, everywhere. They do failure injection, explicit failure injection on every part. And they use formal methods like TLA+. You would have heard of TLA+, which gives you formal proof of distributed transactions and distributed flows and distributed systems. In case you have not, it's highly, I don't know that much. But TLA+ is a very nice way to, it's a very formal way to ensure the correctness of a distributed system, right? A lot of CS researchers use that to ensure the correctness of the system that they are designing, right? So DynamoDB does all of this to ensure the correctness of it, but we won't go deeper into that. Okay, now the next part. Let's talk about availability. Really important for something as big as DynamoDB. So what DynamoDB does is DynamoDB tables are replicated across availability zone. One availability zone is kind of like one data center, right? So one region would have multiple data centers. Let's say in Southeast Asia, you have 5 data centers. In Mumbai, you have 3 data centers and whatnot. So what happens is, what DynamoDB does over here is they run few tests every now and then. Think of it like Chaos Monkey. What they do is they check for resiliency against node failure, against rack failure, against availability zone failure. So if your storage nodes or your API server goes down, if the rack goes down, and if the entire data center goes down, it keeps on checking the resiliency across that. It keeps on checking resiliency against power outages. They own the infra. What if someone just plugged out the power or the power went off due to some reason? They ensure that, hey, their system is still functional even in case of power outage. And resiliency on the data corruption with integrity that we discussed. Now let's go deeper into how do you ensure availability of partition, which is where Paxos come in. You remember where we discussed that table is split into partition. Each partition has multiple replicas, and the partition, the 3 replicas of the partition, they form a Paxos group for consensus. So the idea is that one of them is leader. If one of the node goes down, one of the other node triggers a leader election, and one of these two would become the leader and would start accepting the writes and strongly consistent reads, right? So partition is said to be healthy if you can get a write quorum. Write quorum is what? Write majority. Because when the write comes in, we said that write goes to the leader. It then sends to both of them. It gets acknowledgement from both of them and then returns. What if one of the node goes down? Will it not accept the write? Write majority is what it is waiting for. That hey, out of these 3, if 2 have confirmed that the writes are there, done, I'll move forward, right? So even if one of the node goes down, your writes are still accepted because you still have the majority. When this would come back up, it would take its place, right? It would it would check what all has happened. It would apply those changes on its local machine and would resume its responsibilities, right? So availability of partition is so important with consensus, right? So this is where your Paxos and the rafts come in. DynamoDB uses multi-Paxos for that, right? So Paxos across partition. So which means if you have 1,000 partitions, there will be 1,000 Paxos groups, one for each partition and its set of replicas, right? Okay, that's availability. Now, really interesting part is gray network failures. Now, gray network failures are network failures which are not really failures. So you think that things failed, but it did not actually fail. What happened is there was a connection problem. So you think, let's say a follower thinks that a leader is down because it could not get the heartbeat from the leader. The follower thinks that the leader is down, but leader is not down. There is this network issue that is happening. This is a huge problem because your follower thought that the leader died, but leader did not die. Follower's message just could not reach the leader due to a network issue. So what's the consequence of this? Your follower would initiate a leader election, but the leader is actually fit and fine. How do you solve this? This is a very tricky problem, and it's a very common problem in distributed system, because now what happens is follower makes a call to the leader, does not get a response. It thinks leader is dead, but leader is fit and fine. It is accepting the rights from other places and getting things done. While this follower initiates a leader election, what if this follower initiates a leader election and it also becomes the leader? Split brain problem. How do you do it? Solution is very interesting, very simple. So, to solve this gray network connection problem, what it does is DynamoDB says before any follower initiates a leader election, what it would do is it would check with other follower, hey, do you also think that leader is down? That's what it does. So all the followers of a particular, now here it's at a partition level. Remember this. Partition is where all of this is happening, right? Not at node level, partition level. So the follower, so because let's say I have 3 replica groups, I have 3 replicas for a particular partition. 1 is leader, 2 are followers, right? So if this partition, this replica of that corresponding partition is not getting anything from the leader, it would think the leader is dead. So instead of immediately triggering a leader election, what this would do is it would ask the other follower, hey, do you also think the leader is dead? It says, nah, leader is alive. I just spoke to him. Then it would say, sorry, I will abort my leader election. That's the same thing that happens over here. Hey, distributed systems are very much like humans, FYI, right? So it just counter checks with other replicas to see that a leader is genuinely dead. If this also says a leader is dead, then the new leader election is kicked off. Otherwise, no. So it basically minimizes the number of false positives that you would have, which is precisely what you want, right? Okay, next part, availability, the measurement of availability. Now there are a few very interesting things that would come in measuring availability. So you do basic monitoring of your tables, the number of read requests per second, write requests per second, availability measurement that you typically do, that's there. One very interesting thing what they do is, because DynamoDB is specific to Amazon and it's proprietary, it's not self-hosted per se. So what Amazon does is Amazon wants to measure what customer is seeing that. Who will be the customer of DynamoDB? The person who are on AWS infrastructure, right? But so on AWS infrastructure, what they've done is for all availability zone that they have set up canary apps. Now this canary apps is like a dummy application that fires requests to DynamoDB from that availability zone. So let's say you as customer have hosted your application in AP Southeast 1A, right? In basically one of the data center. So they would have one canary application running there. So which would make call to DynamoDB from this availability zone. So whatever customer would see, that same thing this canary app is also seeing. Not for every use case that I'm saying, but one from each availability zone. This way, your DynamoDB would, like this canary app would keep on registering what response time, uptime, latencies, whatever it is getting, it is observing, it is storing that. So apart from the DynamoDB internal backend measurement that is happening, on top of that, you are measuring what customer is observing, not via injecting in customer code, but running a simple application in the same availability zone as your customer. Simple. But such a brilliant way. Thinking of being customer obsessed is such an important factor of Amazon, and we can clearly see in this design how they are thinking about this. One really interesting thing is DynamoDB is not a standalone service. DynamoDB is dependent on a lot of other services internal to Amazon, right? So all the services that DynamoDB depends on should be more available than Dynamo. Correct? Otherwise, if they are not as available as Dynamo, if they go down, then DynamoDB goes down. So the services that DynamoDB depends on, they have to be more available than DynamoDB. How do you ensure that? So I'll take an example of AWS IAM and AWS KMS. AWS IAM is access management, KMS is encryption, decryption, key management system, right? So for every request that comes in, what DynamoDB has done is, it has listed down all the services that it depends on. It sees that out of all the services that I depend on, is there any service, like for almost every service, I should be able to function even if that other service is down. Let me take an example, which means that my DynamoDB should still function if my AWS IAM is down. How do you ensure that? So what DynamoDB does is caching. DynamoDB caches things locally for some time. So DynamoDB, instead of making call to AWS IAM every time, it basically caches the tokens and the refresh tokens and whatnot locally. So now what happens is, even if AWS IAM is down for some time, until this local cache expires, DynamoDB is still able to function, right? But once this local cache expires, then it would have to make call to AWS IAM, and in case IAM is down at that time, then you are having an outage. But up until then, you are minimizing your outage time. So this AWS does, or DynamoDB does, for all the services that it depends on. So the services that DynamoDB depends on has to be more available than DynamoDB no matter what. But DynamoDB ensures that DynamoDB runs even when the services it depends on are dead. For some time, dead as in it would not be dead for hours and days, dead for minutes. Right? AWS has very high availability thing. But that's what it does. So it locally caches some keys, encryption keys, some authentication tokens and whatnot, so that it does not have to make call to that every time. It is not only just performance boost, but also just minimizes your outage, right? And the final thing on DynamoDB is deployments. How DynamoDB deploys DynamoDB. So why do DynamoDB would need deployment? Because DynamoDB is also a software. So new features, bug fixes, performance optimizations they would do. So DynamoDB deploys without having a maintenance window. So when DynamoDB deploys DynamoDB, there is no outage. There is no downtime. That's the beauty of it. There is no impact on performance. There is no impact on availability. So the way it is rolled out is that there are no problems, no hiccups whatsoever. How do they ensure that? There are a few very interesting things over here. So, plus when DynamoDB is rolled out, you saw DynamoDB has multiple services, auto admin service, router and metadata and this and that. All of them are deployed. Still no impact on performance and availability. Let's take a look on what they do. So first thing first, when anyone has to deploy with confidence, you have to ensure that there is a strong rollback strategy. First of all, have a plan B. In case this goes down, in case this fails, have a strong rollback strategy. Because if you know that this deployment caused the problem, immediately roll back. And how quickly you can roll back determines how minimal your outage would be, right? So that is first thing. Apart from that, DynamoDB does is what canary deployments. Canary deployment is what? Canary deployment is all about deploying things on one server, observing it. If it is all good, then you deploy on other servers. Otherwise, you don't deploy on other servers, right? Plus, you have automatic rollback. So in case you see elevated error rates in your new deployment, immediately automatically roll back without waiting for an on-call engineer to come and trigger the rollback. Right? So with relying on machines to do it, most important. But now, very interesting challenge would come in. Deployments are not atomic. Because let's say you have 4 servers. Let's say while I was deploying on servers, I got deployed on 2 servers, but on other 2 servers, the deployment failed. They are not atomic in nature. So you have to ensure that the code that you are writing is backward compatible. Which means that even if half the machine has new code, half the machine has old code, you would not have any problem. But can you always do backward compatible changes? Not really. Let me give an example. An example of that is, let's say you are writing a new type of message in a message broker. What if the consumer does not have so then let's say you're publishing a new type of message in a broker. So you need consumer to consume that type of messages, right? Now in this case, if your half the machine have code where it is publishing this new type of message or some backward incompatible changes, while other half is changing the old version of it, the problem is that new version has started pushing that message while half of the server is not sending it. So the problem, it's not backward compatible. The way DynamoDB handles that is really beautiful. What they call this is read-write deployment. The idea here is that instead of deploying all the changes at once, split them into read changes and the write changes. The idea being that you should never deploy the write changes unless there is a reader available to read them. So in simple terms, in case of the message broker example that I gave, think of it this way. First, deploy the consumers that have the capacity of handling the new type of messages. And then you deploy the producers who are producing that type of messages. So now you would never have that situation that your producer has produced the message of a new type that your consumers don't know how to consume them. Simple. So splitting your deployment in reads and writes is really essential. This way what you do is you handle everything with grace, because now even if there are some machine that sends the new version of the message, you have the reader available on all the machines that would know how to read that type of messages, and then slowly your changes are getting rolled out to all other machines anyway, right? So what DynamoDB said, that they call it read-write deployment. So they split the deployment. They do the read deployment first and ensure that all machines are capable of handling the new type of data. In this case, the broker example that I gave, and then the writers are pushed as second deployment. This way, they ensure that even though they do not have backward compatibility, you don't still face any issues, any outages, any concerns at all. And this is all about DynamoDB research paper. It was really intense, quite fun, 1.5 hours straight. Quite fun talking about it, but such a beautiful piece of engineering. I just loved when I went through this paper. You get to learn so much from just going through this one paper in depth, trying to understand every single step what happens behind the scenes, right? So yeah, I hope you found it interesting. Hope you found it amusing. I hope it sparked some curiosity of you understanding how distributed systems are built. More importantly, thinking about factors that we typically don't think of much, like deployments, like integrity, right? Like high availability, dependence on external services, replicas, paxos, leader election, outages, all of this at scale, all of these things matter, right? So again, superb paper. I loved it. I would highly recommend you to read it whenever you find time. I tried my best to go through every single aspect of it, and I hope you got value out of it, right? Superb. So yeah, that's all what I wanted to cover in this one. I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.